Alright guys, you're welcome to our next tutorial in the object detection series. Today we shall be looking at the faster RCNN loss function. You recall that we have discussed some generic loss function. We talk about the mean square error. We also talk about the log loss, or what we call the cross entropy loss. Now we're beginning to look at research papers in object detection that makes use of this loss function to be able to achieve, to be able to develop the architecture. So in the faster RCNN paper, you have the definition of their loss function as follows. So if you check here, you will see that in this place we have their loss function defined here. So this defines the loss function for the faster RCNN paper. Now essentially what you have in this place, you have the loss, and you have the probability, and you have the bounding boxes as your input. So, and this is defined in this format. Now we can split this into two. So this is one part, and then we have the second part here. So those two parts are added together. So this is one and this is two. So we have a composite loss function in this paper. So you see that it is added together with a plus. So let's break it down and begin to see what's happening here. Now first of all is we can quickly see here that this is a loss function for the classification. That should be very simple for us to understand. When you do build a classification model, you essentially they are using the example of binary classification here, which you can easily generalize to more than two classes. So you have for instance a class of maybe damaged or undamaged, or you have a class of 1 or 0. So those are the two classes. So you have your ground truth, which is the asterisk one. In this case, this P stands for the probability. It stands for the probability of that now we are dealing with object detection, that the anchor actually contains an object. So the P asterisk is the ground truth probability. That's the ground truth label, which is a probability that the anchor box contains an object. So if the anchor box contains an object, P will be 1. If it does not, that will be 0. Okay. Why? The Pi is the predicted probability of our model. The probability, the prediction probability of our model, saying that an anchor box actually contains an object. Okay, so what do we want? We want our model to be able to give us a probability of as close as 1 if the ground truth says the probability of the anchor box is 1. Okay, and otherwise. All right, so we do the normal thing that we saw in the log loss, or the cross entropy loss, which is we sum over all the anchor boxes. So we sum over all the anchor boxes in our mini batch, since we take a number of batches. So after we have sum over, then we normalize by the number of classes. So the NCS, that will be the number of anchor boxes that we actually, excuse me, it's not number of classes, by the number of anchor in the mini batch. That should be our NCS. So in their own case, it is 256. So you normalize by that. Is normalized by the mini batch size. So that is the number of uh, uh, so that's the number of their mini batch. That's the number of the mini batch. That's the mini batch size. So you normalize by that. That's for the first part of the loss function. Now the second part of the loss function is for the bounding box. Now, so this takes care of the bounding box prediction. As usual, the asterisk is the vector of the ground truth, while this T is the prediction vector of our model. So we try to get the loss between that. How well is this prediction of our model close to the actual ground truth? And essentially what they use in this paper is L1 loss. Let me check that. They use an L1 loss for that. They use L1 loss, that is to be able to get the prediction for the bounding box. Okay, yes. So what they use is the robust loss function, which is the smooth L1, to be able to define this difference between the actual ground truth box and the prediction. Now, there's something interesting that they did here, which is that they multiply this loss with the probability, the ground truth probability. And the essence of doing this is there is no point doing any work measuring the loss when actually the particular instance of the bounding box does not contain the object of interest. It will be a wasted work trying to do any calculation. So because of that, they threshold this based on the probability of the ground truth. So if this probability is 1, then that means that the anchor box, that instance of I, actually contains an object. Then it is a good work for us to measure how far is the predicted boxes from the ground truth boxes. But if the probability, the ground truth, is actually 0, then all this becomes 0 and there's no need to do any calculation. Likewise, we have this NREG, which is normalization parameters for us to normalize this. And we have this lambda, which is a regularization parameter. And you can see the details here. So their NREG is defined as is normalized by the number of anchor locations, which is in their own case is roughly like 2,400, and they set the lambda to 10, so that the CLS and the REG can roughly equally weighted. So it's just the normal thing that you see, like doing some kind of regularization to make sure that you have the numbers in each of those two loss functions are roughly the same. You don't have I number in one side, and you don't have one side of the loss containing very high number and the other side containing very small numbers. You want the range of the numbers to be equally the same. So they try to normalize this this so by multiplying this by 10, so that it will be in the same range as this first part. So that's essentially what is happening in this in the loss function. The classification loss is log loss, which is the cross entropy loss that I mentioned. So you can just key in this pi and p star into the cross entropy loss that we have earlier discussed. That's essentially what is happening in the faster RCNN loss function. We've talked about the region proposal network, and we have an anchor, and so we try to use the loss function to be able to refine the anchor as to whether it contains an object or not, and to make sure that it matches the ground truth as much as possible. So we assume a positive label to be of two kinds of anchors. The anchor with the intersection over union with the ground truth. So first of all, check anchor. We have a certain number of anchors that are predicted, and we check how well it is that it matches the ground truth. So we choose the one that has the highest match. Then after that, then we can then try to choose an anchor that has the has an IOU overlap greater than 0.7 with the ground truth, with any ground truth box. And the essence of doing that is to make sure that the predicted box is as close as possible to the ground truth. So that's essentially what is happening here. The details of the different coordinates of the bounding box is given below. So to get the bounding box coordinate, you have the x, the y, the w, and the h. Essentially, the w and the h talks about the width and the height of the bounding box. So if you are predicting a bounding box, you want to predict how wide should it be and how high should it be. So that is what the w and the h is doing. And the x and the y is just trying to predict the center coordinate. Where should it be centered from the entire image? So how far should it be from the x-axis, that is from the border? How far should it be from the left? And how far should it be from the right of the entire image? Because you are going to draw the bounding box in an image to locate an object. So that's what's happening in this. Okay, I hope someone will have benefited from this discussion, and to show us what essentially happens in the object detection state of the art faster CNN and the implementation of their loss function. It's simple and very intuitive. Oh, thank you very much for listening. Do give us a like if you benefited one thing from this, and hope to see you in the next one. Thank you.